Okay, so there's a lot of questions about how to calculate the isoelectric point of a polypeptide, and I've been getting it a lot, so I'm just making this video to just send this when someone asks for it. So here's just a quick example, which I'll be going through most of the stuff. I have chosen 3 amino acids to push together, like link together, and then we'll calculate the isoelectric point of the polypeptide. And I've already written the pKa values for each amino acid because it will be important eventually. But at this moment, what the main focus is now is to just get this all 3 of these amino acids into one polypeptide. So I'll quickly do that and then I'll be back now. Okay, I have now pieced together the polypeptide, the amino acids, into one polypeptide chain. And here is leucine. Then from this NH to here is our serine, and then this is our valine that we had all just pushed together. Now, one thing everyone has to remember with something like this is these pKa values become irrelevant. They have no like doing in the polypeptide chain anymore because they aren't. Let me put it like this: the hydrogen atom can't give it up unless the whole polypeptide chain breaks apart. So these pKa values aren't important anymore, these two, well, 4 actually, because they link together to form the whole polypeptide, so they don't have an influence anymore. And then after we've pieced together our polypeptide, you'll see there's 3 pKa values left. We all know that there will only be a minimum of 2 pKa values. So that means our amine group here, our first amine group where the polypeptide chain started, that will always keep a pKa value, and our our alcohol piece here will also always have a pKa value. And then any other side chains or side groups that has a amine or an alcohol will also have a pKa value, like serine has a alcohol group added with a pKa value of 13. Usually with serine, because the pKa value is so high to 13, that we don't really account for it, because the chances of, let's say, our pH going above 13 or 12 is not really a lot. It's not something that we see. So yeah, that's why trying to find a pKa value for serine is a bit difficult. But now this whole polypeptide chain is together, and we can basically see this whole thing as one amino acid, if you want to put it like that. Like, let's say we have a pH of, let's say, 3, then we have to look, okay, this is our normal, completely saturated with protons amino acid chain. So that means all of the hydrogens are filled in, everything is in that needs to be in. We are at the lowest pH, so that means all our hydrogen stays. And like we know, the higher the pH goes, the more hydrogen atoms we lose. So at this moment, this is a normal, but like normal, there's also a pH that determines how many hydrogen atoms there will be in each group. So with our amine group here, there's only 1 hydrogen that can be lost. Then this is also positive, have to remember that. So basically with this here this is our normal. It can only lose 1 hydrogen, and the same is with the oxygen. So let's say we are calculating the isoelectric point of this amino acid at a pH of 3. Now our amine group here is going to keep its hydrogen atom because its pKa value is higher than the pH at 3. But this OH here, the pKa value is lower than 3. So this hydrogen atom will dissociate and not be linked to this polypeptide, which will give us actually a negative side here. So what we are actually then seeing here is we are seeing, okay, our +1 charge of the amine group and our -1 charge of the alcohol group will then give us a net charge of 0. And this means the polypeptide chain is in our Switzer ion. And now what we see here is we then have to calculate the Pi. And our Pi is essentially just our pKa values added together and divided by 2. But those pKa values are usually where the Switzer ion is in, meaning where the net charge is negative. So because we are in a Switzer ion position, does that mean we end up with these two as our pKa values? Because between these two values is where our net charge will be 0. So I'll like do another example at other pH, just to like show what is actually going on. Then we say plus 9.60 divided by 2 is gonna give us, let me just get my calculator. Okay, I did the equation quickly just on my calculator and it gave me 5.96. So this is then my Pi value for this amino acid, and that's basically how you calculate the isoelectric point of your amino acid. And it's not the same with each polypeptide chain. It is always dependable on the like way everything is put together, which ways your amino acids link together. Like the serine and leucine can switch places and it will be able to change the Pi value, the isoelectric point here. And honestly, I think to understand this, you also need to understand how to calculate the net charge of a polypeptide. And it is as simplistic. I did do it right now, but let's give it another factor. Let's say we are at a pH of 10. Okay, this is our amino acid. Now our pKa value for the alcohol group here, the OH, is lower than 10, so we are still going to lose this hydrogen atom here, and it's going to be negative here. And now the amine group here, our pH is larger and higher than our pKa value for the amine group. So that means this H plus is going to just become, well, H3 plus is just going to become a H2. It's going to be neutral now. So essentially what is happening now here is we are going to end up with a net charge on the polypeptide of basically just negative, because if we take in account the pKa at the, let's call this 1, 2, no, 3, 2. Okay, I made that 3 because like I said, the serine OH won't really dissociate that easy. It's not something that's going to happen all of a sudden, because getting to a pH of 13 isn't all that easy. It's hard actually. And not just that, getting to a pH that high is, but yeah, just on its own a lot. So let's say our pKa1 here, okay, plus our pKa 2 plus our pKa 3. Now what we're going to see here is if you add these pKa values, okay, what we are getting at the moment, then it's going to give us our net charge. Now not these pKa values, not the 9.6 or the 13 or the 2.32. It's going to be the charges that they give off, the charges that those pKa's are going to give off. So with our pKa1 value, if we are at a pH of like 1, let's say 1 or 0, where all the hydrogen atoms are saturated, all the hydrogens are in place where they need to be, stuff like that, then this is going to be a NH3 plus. Okay, so this is going to give us a +1 charge. This serine here, it doesn't have a charge. It hasn't lost its hydrogen. It's saturated. So this is going to give a net charge of 0 at this area. And then this OH here is also still going to be a net charge of 0 because the OH doesn't give a charge to the complete polypeptide. But now we are going to a pH of 10, which is higher, and now we have to look at the pKa values of each of these groups, these ionizable groups and stuff like that. So with our alcohol group, we will see our pKa is 2.32. Okay, this pKa value is lower than the pH, so that means it's going to lose its hydrogen atom, giving us a negative charge here. Now let's just fill this in our place here. So our pKa2 value is then -1. Yes, you still say plus, we just put this in brackets. Okay, so our pKa2 value is negative. Then we go to our next lowest pKa value, and we're gonna see, okay, it's this NH3, our amine group, which is 9.6. Okay, now we put in and we check, okay, is this pKa value higher or lower than 10? Okay, well, it is lower. And with that being said, that means it's going to lose its one hydrogen atom, and it already has a positive charge to it, so it's not a positive charge, it's a neutral charge. So it's going to give us a H2, and that's that. It's not going to be negative, it's not going to be positive, it lost a charge, so it's going to be neutral. So with our first pKa value, then we just say 0 here. Okay, and then our next charge is the serine group, which is at a pKa value of 13. 13 is higher than our pH, which is 10, which leaves us with a net charge of 0, because yet again, it's not positive, it's not negative, it's neutral. And this is going to give us in total a negative charge of 1. That is our net charge, essentially. That's all we actually get. And it is extremely easy. It's just reading about it is a bit harder than explaining it.